Okay, up to this point, we've been focusing on the force of gravity, but there's another half to the mechanics of how objects move around when gravity is involved. Okay, so in addition to thinking about the force, we can also think about the energy. All right, and so the approach that I want to use for this is, let's imagine that there is a planet, like this, and let's say that there is some object that we're going to move around from some point to some other points. All right, so I'm going to define my coordinate system to start from the center of the planet, like this, and then I'm going to have R1 out here. So this is the position of the object relative to the center of the planet. And I'm going to imagine that this sets up my axis, and so r hat vector is going to be to the right. All right. And let's imagine that an object is going to move from R1 to R2. Okay, so from some position to some other position. I'm going to, in this case, have it move to the right. Okay, so there are multiple ways to think about what's going on in this situation. So what I want to do is I want to imagine that the object is at rest at both times. So the object is at rest at R1 and R2. And an object would not just spontaneously go from some position to some position further away from a planet. That's not what we would normally expect. So what I'm going to imagine is that I have some external agent, which I'm going to draw as a hand. Okay, so here's a hand. And the hand is going to pick up this little object and move it to a new position over here. Okay, so based on this, we have some external work that is done by that hand. And the work that's done on that object is going to be equal to the change in gravitational potential energy of the planet object system. Okay, so by moving this object further away, the hand is adding energy to the system. It's doing that work. Okay, and the amount of work it does is equal to that change in energy. We can tell it has to be true if the object is at rest both places. The only kind of energy that can change is the potential energy. Okay, well, we can calculate that work. So the work is easy enough to calculate. The definition for work is that it is the integral of the force dotted into the displacement for some motion. All right, well, in this case, the displacement is going to be in the r direction. So the object is moving to the right. And for the hand, it is exerting a force that's to the right. We can tell that has to be true because if I draw a free body diagram for the object, I've got a force on the object by the hand, and that has to balance out the force on the object by the planet. If the object is moving at a constant speed, it's not accelerating, so all forces are in equilibrium. Those two forces should be equal to each other. So the hand's exerting a force to the right, the displacement's to the right. So that simplifies F dot ds. Okay, what we're going to have then is, well, based on my argument that the force from the hand is the same as the force from the planet, its magnitude is going to be equal to g times mass of the planet times mass of the object over r, which is a variable, so r is changing as the object moves, and the direction is going to be dr, because it's moving to the right. If the hand were moving the object in the opposite direction, then there would be a minus sign from that dot product, but here we have no minus sign because they're in the same direction. Okay, and the integral is going to be evaluated Newton's law of universal gravitation as a squared. Okay, and the force is evaluated from R1 to R2, so just the starting point to the ending point. And if you go ahead and do the integral, well, g and the masses are constant, so you're just integrating 1 over r squared. And what you get is going to be negative g times mass of the planet times mass of the object over r. And that's evaluated from R1 to R2. And remember, that's equal to the change in the potential energy. Okay, so we can see, since we're taking gmm over R2 minus gmm over R1, you can just associate that difference and get that u grav is equal to negative g mass planet mass object over r. And because we've only defined the difference, we could also add, if we wanted, some starting energy, which we usually don't. There's not a lot of reason to do that. Sometimes that might be a thing you would want to do, but typically that only complicates the problem. Okay, so we have this expression for the gravitational potential energy. Okay, so there are a few observations that I want to make about that. So first of all, notice that u grav is always negative. Okay, so how does that make sense? Well, if you think about it, even when we were using u equals mgy back in 121, we could still have negative values for that potential energy. You know, you pick some starting point for y. Typically, you can pick it to be at the lowest point in the problem, or at some point where you're confident that y will never be negative. But nothing bad ever happened if y was negative. We could have a negative potential energy and just go about our business, and everything worked out just fine. Because all we're ever interested in is differences in potential energy. You know, noticing back up here, what we defined was the difference in potential energies. That's all that can ever have a physical meaning. Okay, the actual value doesn't. So if we wanted to make the potential energy be positive, we could just add some arbitrarily large constant, and then it would be positive. But nothing bad happens if it's negative, since all we ever care about is changes. A nice thing about this expression is that u grav goes to 0 at r equals infinity. So if you get far enough away, we can think of the gravitational interaction as going to 0. Both the force goes to 0 and any gravitational potential energy goes to 0. So that means that we can ignore stuff that's far away. That's a thing that is really nice to have. We only have to worry about stuff that's relatively close. Also notice that the gravitational potential energy is calculated between pairs of objects. So u grav is calculated pairwise. Okay, so if you had, let's say, a constellation of asteroids and there were 5 objects, if you wanted to calculate the gravitational potential energy of that system, you would have to calculate the gravitational potential energy for each pair. So between 1 and 2, between 1 and 3, between 1 and 4, between 1 and 5, and then you'd go on and do between 2 and 3, between 2 and 4, and so on. So after that point, basically we can use this expression for gravitational potential energy in the exact same way that we would have used mgy. So for instance, conservation of energy is still satisfied. So conservation of energy is still true. Okay, so for example, you could have some starting potential energy plus some starting kinetic energy, and that'll equal some final potential energy plus some final kinetic energy. Okay, and this works exactly the same whether you were using MGY, really close to the surface of the Earth, or whether you were considering interplanetary distances and you used negative GMM over R. Everything works exactly the same. You're just doing the algebra to solve for, the speed or the position or whatever it is that you're interested in.